To LeetCodePaths Pro. Um, yeah, had a bit. Hopefully, all had a good Thanksgiving. Today is Friday, November 24th, day after Thanksgiving. Um, yeah, I've been kind of doing some studying of some DP concepts. So now I'm going to try to tackle some of these DP problems again. I also watched a NeetCode video on this problem. So he kind of goes over that solution I did kind of hastily in that last video I recorded, and was like, oh, I don't really understand this. So I kind of try to explain what's going on. Right. So his figure that he drew is really good. So right, you're starting here. You're at 0. Then you go 1 step, 2 steps, 3 steps. He also used 4 steps, 5 steps. So right, this is 5, 4, 3, 2, 1. Right. He also used 5, n equals 5 as his example. Because if you'll notice, anything n equals 3 or below, right, if n less than equal to 3, turn n, right, that, like, if we just run that on the local test cases, right, that works. So when we get to the values greater than 3 is when we actually have to start doing some stuff. Yeah, so basically the idea here is we're creating a DP array of length n, right? So in this case, it'll be length 5. So 2, 3, 4, 5. All right, and how we can do that is something like this. And we'll just initialize it to, I think 1, right? Kind of explain why. Right, so the idea here, right, is that we're basically going backwards. We're going, like, this is a bottom up. So in DP, there's a bunch of different, I don't know, like DP algorithms, I'd say. There's like knapsack algorithms and common subsequence and stuff like that. And like Kadane's, I don't think Kadane's algorithms technically DP. Nah, let's see. I don't think it is. Oh, it is. Yeah. So Kadane's algorithms are DP. You got like palindrome. You got knapsack. I think I already said that. Like greedy is kind of concept similar to that. But there's like two bigger branches in that. You have bottom up or top down DP. Top down is like, okay, how can we solve this problem recursively? Just brute force, and then adding caching, adding memoization. That's top down DP. And a lot, like, some people don't consider that to be DP according to NeetCode. And then bottom up DP is like more true DP, right? Where you're using a base case, and typically it seems like you're kind of working backwards from that base case, right? So here we're working backwards. Yeah. So it'll look something like this, right? Where from 5, right? We know, okay, we're there. We hit it. There's one way to get to 5, right? If we're at step 4, we know there's one way to get to 5 as well, right? We can take one step. So we can pre-fill these two to 1 and 1, right? If we go down to 3, we know, okay, if we're at step 3, how can we get to step 5, right? We know we can take a hop here, or we can take 2 hops here, right? We can get to step 4, which we know from step 4 there's one way to get to step 5. And then we also know that from step 3, we can just get to step 5 another way. So there's 2 ways to get to the final step from step 3. And if you'll notice, that's 1 plus 1 equals 2, right? So this is basically the Fibonacci sequence, if you're kind of catching on. And so then from step 2, like, let's solve this little sub problem. If we're at step 2, right, we can get to step 3 one way, right, which we know from step 3 there's 2 ways to get to step 5, so 2 plus 1 is 3, right? Because we can also, well, we can get to step 3, right? So there's 2, and then we can get to step 4, and there's 1 way to get to step 5 from step 4, so 2 plus 1 is 3, right? I think we have to make it, I think we initialize this 1 extra, right? So say plus 1. Maybe do that here. Do like that. And then right from step 1, because we are assuming we're starting down here, right? We're starting no steps. Yeah, that's the idea. So from step 1, right, we can get to step 2. Step 2, there's 3 ways, which we already calculated. We can also get to step 3. From step 3, there's 2 ways to get to 5, so that's 5, right? And then from on the ground, we can get to step 2. Step 2, there's 3 ways to get to 5. And then we can also get to step 1. From step 1, there's 5 ways to get to 5, so that's 5 plus 3, that's 8. And that is our solution, right? So let's go ahead and try to calculate that. So we could do like for I in range, like the up end, and we'll go backwards, right? And we'll say dp of I equals we don't want to start at the very end, do we? Right, because we'll start here. We want to start here. So do we want to do it like this? Like start like -3? Or yeah, -3. dp of I equals dp of I, and because we're going backwards, it's plus 1 plus dp of I plus 2, and then outside of this we can just return dp of 0. I wonder if that works. I mean, this will run here. We have to see submission if that'll work. Oh. Oh, it's just n. It's just an integer. Let's do that. Output 3. So do we want to start at 2? Yeah. Okay, cool. Okay, I'm really happy with that. Right, because we start at n-1, we start here. We need to start -2. I guess. What? What? Excuse me. Oh yeah, we have get him. Or sorry. If I have an array, Python, what spot will array? So that'd be 5. Okay, so we want to start on 2, I guess, because this will add a 0, right? So that means we can print dp of I, because we should have a 0 if we need to make our own test case. I plus 1 print I plus 2. So 3 is I. So it starts at 0, 1, 2, 3. Oh. Hmm. 1, 2, 3. Do we just print dp? See what that looks like. 1, 2, 3, 4, 5, 6. Yeah. So 3 is I, 0, 1, 2, 3. I's here. I plus 2 is 1. But if n minus 1 gives us this, oh, because it's n minus 2. Oh, so this is 5 minus 2. So it's 3. Ah. It's not the length of dp, right? Because if we did it, oh. Interesting. Okay, I see why that is. So we can get that out of here. All right, so, okay, cool. Got that working. And then what Nico does in his video, right, you'll notice we're only ever using the two previously calculated values to calculate the next value, right? And then here, we're using these two to calculate this. So we don't need a whole array. Why have a whole array, right? Save some memory, because right, the solution of this, or the runtime of this is O of n. Space is also O of n, right? Or we can do better, right? So we just need two variables, right? We can have variable. He uses 1, 2. I think that's kind of confusing. Go on this previous. Maybe that's not better, but that's what I'm gonna go with, right? These are gonna be 1, 1, right? And in this case, we don't need to go all the way, right? What we're gonna do, so same idea, but we have previous, we have PP, we'll call it PP. We have P and PP, right? And we're looping through I in range n, right? So basically this is like, it's like this way. We'll draw it this way. And we have 1, 1, and we have P, PP, and and I think we might need to mess around with the range, but and we'll probably want to return P, right? Or probably return temp maybe. I don't know. We'll see. So the idea here is well with temp was attempt to PP previous we'll say, we'll set it to previous. Then we'll say previous equals temp plus previous, right? And previous equals temp, right? And we want to return previous. So if we run that, I mean, it'll work for these three test cases, or these two little test cases, but now the real test is submitting it. It's not working. So yeah, we want to do endless. I think we are going too many times. Cha-ching, money. Right, because basically what we're doing, we're saying, okay, temp, you're going here, previous, you're going to be the next iteration of this. We're going to say you're going to be temp plus pp, so you're going to be 2, and then we just move pp up to temp, right? And temp's going to get overwritten in the next loop iteration, right? And we want to do this 4 times. Just print I. Right, we'll see. I gets run 4 times. Awesome. Right, starts at 0. 1, 2, 3. Yeah, runs 4 times. Yeah. Cool. So this is the bottom, the two, like the kind of the most optimal solution. Right, because top down, you're recursively, you're doing a recursive call stack, so that's going to have some memory as well. But I want to try coding up the recursive and then using memorization. Right, so we'll use a cache, or we won't first, right? So we'll say that we'll define our helper. All that needs to get passed in the helper is, we'll call I. Yeah, I. We'll say if I equals n, can return 1. Right, because we're just counting paths. What are we doing otherwise? Else, we just want to call helper of I plus 1, or helper of I plus 2, right? I don't think that's going to work. We can try, and we can just say return helper. And yeah, we have to set I equal to, just set equal to 0. Let's try. Yeah, we'll try that. Return helper of I. So we need some more things going on here. What if I equals n? Yeah, we're going to try one. Else. So if I is greater than n. return 0. I don't think I'm calling this right at all. Was two-step. Oh, can you not? What is that? I've never seen it before. Can you not put numbers? Oh, sorry, this is what's that? Yeah, I'm just gonna run locally. Oh. Something like that. Break outside. Let's see if we can find somebody who did this. Ah, here we go, recursion. So that guy's doing recursion. Right. Oh. So we do need to do it differently. Yeah, you gotta call. Oh. Different. This is what. This is more what I was looking for. So you do want to do like backwards, right? I see. All right. So it worked to run. If we submit, it should work too. But it runs out of time. Interesting. Does this run out of time? I wonder. I wonder if this will speed that up. Let's hash this out. Interesting. So this is too slow still. Oh, time limit exceeded. Ah. Okay, so I did like that other solution more. It was a little more intuitive for me. But let's do it like I like it like okay. And then use a dictionary. Say, what do we say? We'll call it cache. And we say cache of 1. It's a little, then cache of 2 also equals 1. Or sorry, equals 2. So now we check if any cache of n. Okay. Else, then we want to store our calls. Interesting. You see what I mean with the memory? Right, so what's going on here? This is pretty cool. So we got our cache. It starts and it's got 1, 1, and 2. Does he talk about what the and then our client, we want to return a climb of n and say n equals 5. N is in cache, fast, not cache. Otherwise, cache of 5 equals climb of, we're making a call at 4 and 3, right? Neither of those are in our C. So we start like up here, 4 and 3, right? Then otherwise, saying cache of 4 is, and we also, we're also trying to put 4 on the table. Oh man, this is confusing. It's gonna be confusing to draw 4, n minus 1, 3, or n minus 2, right? Okay. So we call it, so we go back up. N minus 1, if n is in cache 3, it's not in cache. So cache of n. So v2, 1, n is in cache 2. 2 is in cache, return at 2, so now it's coming back up. Plus 1, so cache of 3 is 3. Oh, so these are just like the straight up values. Alright, okay. And then Now we know the value of 3. Now we look at, okay, this is still our recursive call. What is the value of 2? 2 is in our cache. 2 plus 3, so 4 is 5. Right. 4 has been filled. Now we look at 3. 3 is now in our cache. 3 plus 5 is 5. It's 3 plus 5 is 8. So 5 gets filled with 8. And that was our original recursive call. And so we return cache and the value associated with that original recursive call, which was 5. N was 5. So 8. Okay. Very cool. Very cool. Oh boy. Oh, it's slow as hell that time. But yeah. Thank you. Thanks for watching, guys. See ya.